Alright, in this video we're going to solve another example involving Green's theorem, and basically what we're given here is the following line integral. We have 3x to the power 7 plus 6y times dx, and then we have 3x minus e to the sine of y squared. And we're told that c in this case is just going to be the curve that surrounds a circle centered at the point 1, 4, so that's the center of the circle there, and it has a radius of 2 essentially, so we have 2 squared here. So the first step in solving this is going to be to identify the two functions here. So we're going to write fx is going to be equal to 3x to the power 7 plus 6y, and then we're going to have fy equals to 3x minus e to the sine of y squared. Now, in order to apply Green's theorem, we know that we have the following relation. So for a closed curve C, we have the vector field times some dr element, and this is going to be equal to the double integral evaluated on the enclosed region D. And now we're going to have the following expression. So we have fy differentiated with respect to x, and then f of x differentiated with y over the whole area of that region, dA. So in order to apply Green's theorem, what we need to do is differentiate these two. So we start off with x with respect to y, so this becomes 6, and then we differentiate the other function with respect to x. So this is going to be equal to 3. So it turns out that by doing this, our expression is going to simplify greatly. So we're going to have the double integral of the region D, and now we're going to have this here minus that, so that's 3 minus 6 over the whole region of integration dA. And now this is going to simplify to the following. So we're going to have double integral on the region D, and this is going to be minus 3 dA, and we can take the constant out, so this is going to become minus 3 times the total integral over the region D times dA. And now we can easily try to apply some limits on here, so we can convert this problem to polar coordinates and then apply the limits and evaluate this. So normally what we would do is say dA is equal to r dr d theta, and then we would replace x with r cosine of theta, y with r sine theta, wherever we may find them, and then we would try to find the limits on r. So let's say a to b, and then on theta, well, what would be the total? This covers 2 quadrants, so it would go from 0 to pi. Now the problem is that because this circle is not centered at the origin, the limits for r are not going to be constant. They're actually going to be functions of theta, because what we have here is essentially just a polar curve. So this would actually be quite complicated, but we can simplify this problem further by identifying the fact that this double integral here is simply the area of the region of integration. And we know that this is just a simple circle, so this is just going to be equal to the area of the circle, which is pi r squared. And we know from this equation that the radius is 2, so this is pi times 2 squared equals to 4 pi. So now if we put this in here, it turns out that the integral, so we have fx dx plus fy dy is going to be equal to minus 3 times 4 pi, which turns out to be minus 12 pi. And that's it, that's the final answer. So you see how applying Green's theorem once again, we found the answer to this rather complicated line integral simply by casting the problem into a double integral, and we didn't have to do any substitution for dx or dy or any parametrization for that matter. In fact, we didn't even have to use any limits of integration, because we just used the argument that this quantity is just the area of the region D, which is the area of the circle, and this allowed us to essentially find the answer rather quickly. So this is one of the very powerful applications of Green's theorem, but of course the limitation is that it only works for functions of 2 variables.